Okay, so in section 12.5, they talk about applications of double integrals. And double integrals have many different applications. One of the applications, actually, of double integrals is to compute, uh, to compute the probability involving what's called a bivariate normal distribution. And they have an example. I talk about probability in example 5 and in example 6. They even talk about expected values. So that's basically leading into statistics, probability and statistics at the junior and senior level. And and then there's a whole courses on this. This is my area of expertise, is probability and statistics. Well, statistics particularly. The book has nice examples on that, and I'm going to focus a little more on the concept of moments and centers of mass, because I think before, how many of you have told me that you've seen moments, work with moments? Okay, Christopher's seen it in class, his class, and in physics, Thomas has seen it. So, that's an area that I do think I need to definitely discuss. So they mention here that we've already seen applications of double integrals. One application is computing volumes. Okay, another application is finding areas of surfaces, and we're going to talk about that on Thursday. In this section, we explore physical applications such as computing mass, electric charge, center of mass, and moment of inertia. How many have maybe seen moment of inertia in one of their classes? In a physics class? Okay. Christopher and Ryan have. All right. And wow, both Christophers. So we see that these physical ideas are important when applied. Well, these ideas are important. So I want to just give you a little guided tour of section 12.5, but I want to bring up the whiteboard just for a moment. So density. Okay, density we denote by the Greek symbol rho. Okay, and how is density defined? How is density defined? Maybe you learn it. Okay, that's right, Marvelous. It's mass divided by volume. Mass divided by volume. So the normal density that you're used to thinking about is units of mass per volume, per unit volume. But you can also treat density, and they do this in section 12.5, as mass divided by area, the area of a lamina. Okay, how many maybe have seen this kind of treatment in density in one of their courses, in a physics course? Has anybody the center, the moment, the center and mass of a lamina? Okay, all right, good. Excellent. So in this sense, you could think of mass as density times area. And I'm writing this here because it's going to be a nice way of helping you feel a little comfortable with section 12.5. So if I go back to the ebook here, okay, and if you double click on it, it'll make it a little bigger for you. They mention here about density and mass, and right away they have the density. Whoops, hold on, I always get that wrong. they have the density as mass over area, okay, effectively, okay? And in the picture here, I want to really get to this one picture here. So, well, hold on here. Yeah, this is what I want to get to. So, if we wanted to find the total mass of a lamina, okay, total mass of a lamina, and the lamina is basically something like this in figure 1. Well, you could, if the density were a function of x and y, in other words, on that lamina there, in this, hold on, I want to make sure it all shows. Hold on. In that lamina in figure 1, okay, you have a region D, which is the region for the lamina. That's the lamina. And you have coordinates x and y, and there are different coordinates of x and y on the lamina. And every coordinate on that lamina could have a different density. You could allow for a different density. And if you were to do that, then the mass of the lamina, hold on, the mass of the lamina would be equal to the double Riemann sum of the density at each point divided by the piece of area at each point. Okay, and so this here, this idea of mass, then if we take more and more points on the lamina, okay, then the mass would actually be equal to the double integral of density times density dA over the region D. It's that simple, class. It's that simple. It's really that simple. So, are there any questions on that? Okay, well, let's go down a little bit then. So, they mention that physicists, okay, physicists also consider other types of density that can be treated in the same manner. For example, if you have electric charge that's distributed over region D, and you have a charge density, okay, it's units of charge per unit area, given by the function sigma xy, then the total charge would be equal to the double integral shown here in equation 2. Okay, all right. So, you know, double integrals are allowing us to study a variety of applications. And in the book here, if we look at example 1, they say find charge by integrating charge density. Okay, so they have in the example, okay, that charge is distributed over a triangular region in figure 3, so that the charge density is x times y. Find the total charge. Okay, and so given this, well, figure 3 is right here. Okay, there's a region D in the xy plane. And based on the picture in figure 3, based on that blue arrow on region D, are they going to treat this double integral problem as a type 1 or a type 2 region? Based on that blue in figure 3, that blue line with the arrow on it. Good, it's a type 1. Now, could this be treated, could region D be also treated equivalently as a type 2 region? Would it cause any more work to treat this region as a type 2 region? Could we compute the charge? Could we compute the total charge with just one double integral? And that's right, Ryan. The answers we could. So there's no more work involved. Okay, so you could treat this triangular region in figure 3 as a type 1 or a type 2 region. But intuitively, we tend to, if we have a choice, we tend to go with the type 1 region. So here is the charge then. So if we go back to the triangle here, the triangle, the bottom function is y equals 1 minus x, the bottom bounding function, and the top function is y equals 1. And then the limits go from 0 to 1. So based on that, here's how we would find the charge. Okay. Are there any questions about what you're seeing here? Are there any questions at all? Okay. Well, that being said, let's move on to moments and centers of mass. Moments and centers of mass. Now, at least at Montgomery College, in Calculus 2, one of the applications in section 6.6 is finding the center of mass with a constant density. Okay. Here we can consider a lamina with variable density. Okay, variable density. And if you, I want to say this the right way, class. One moment. One moment, class. One moment. Let me just. If you, I have to go back here. They talk about figure 2. They talk about figure 2. And figure 2 is where they take a region in the XY plane, and they have a coordinate, and they have, you know, the little region. They take the region and break it up into little rectangles. And the more rectangles you take, the better. And if we do that, then it turns out that we can approximate the moment of every rectangle about the x-axis by this product. You take the density at the point times the piece of area at the point and multiply it by y sub ij. Okay, that is going to be the distance that coordinate is from the x-axis. Okay, and so based on that, you can find the moment about the y-axis by taking the limit, and you're going to get a double integral over region D of y times the density dA. Okay, that's what you're going to get. So see, we can well, given double integrals, we can compute moments over a wider range of regions in the XY plane than what we could do in section 6.6. Okay, so now let's talk about then the moment about the y-axis. Well, moment about the y-axis would be a similar formula. It's just instead of x times rho in the integrand, you're going to, instead of y times rho in the integrand, you're going to have x times rho in the integrand. Okay, so those are your two moments. Okay, and then if you want to find the center of mass, okay, what you need to do is you need to take your, okay, this is sometimes called a centroid. You take your moments about the y-axis and the x-axis and divide that by the mass. And that's how you're going to get your center of mass. So it's like the balancing point. If you think of, like, you know, take your lamina and figure, well, hold on here. Let me make sure everything's showing well. It's absolutely fascinating, really. If you take your, in figure 4, okay, take your lamina, okay, and remember the lamina could have differing density depending on what coordinate you are on the lamina. The balancing point of the lamina would be at that center of mass, x bar, y bar. Okay, and so they have an example, but and we'll look at example 2. But are there any questions so far? Okay, well, let's look at an example. So really now, you know, with sections, you know, 12.2, 12.3, and 12.4, you have the ability to compute a lot of different double integrals. And section 12.5 is just an application. You're looking at application. So here, in this example, okay, hold on, let me highlight it. Example 2, they want you to find the mass and center of mass of a triangular lamina with those vertices and that density function. So of course, what you have to do is, as always with these problems in chapter 12, you have to find your region D for your integration. You have to get your limits. So you have to draw a picture. So certainly on the exam, I'm going to be expecting to see a lot of pictures for problems where you have to come up with the limits, right? I mean, you can't get the limits without having a region D, right? And so, okay, here's that figure 5. Here's the triangular lamina with vertices 0, 0, 1, 0, and 0, 2. And of course, the line segment connecting 0, 2 to 1, 0, well, they say, okay, y equals 2 minus 2x. Oh, how did they get that? Well, they used the point slope formula. Y minus y sub 0 equals m times, well, no, first of all, they found the slope of that line segment, and the slope equals -2, using the slope formula and the two vertices there, 0, 2, and 1, 0. And then from there, they used the point slope formula, y minus y sub 0 equals m times x minus x sub 0. Okay, so not hard. And then it's clear the bottom function, about below the region D, is y equals 0. Okay, so they go ahead then, and right away they compute the mass. Okay, and here are your limits, and they do dy dx. They're treating that triangular lamina as a region 1, as a type 1 region. You get 8/3 for your mass. And then, I mean, are there any questions so far? Okay, well, let's continue on. And then x bar and y bar, okay, which is your coordinates for your center of mass. Well, x bar is, they just use the formula and compute out what x bar is. X bar is 3/8. Okay, and then, so, I mean, you know, the mass was equal to 8/3. So 1 over the mass is 3/8. And you work it out, and interestingly enough, x bar is equal to 3/8. Okay, that's the coordinate for x bar. And then for y bar, okay, they they go ahead and compute the y bar coordinate for the center of mass. And again, it's just really applying the formula. Okay. And let me just see here one moment on this. Yeah, you get 11/16. And so it turns out that your center of mass is going to be equal to 3/8 and 11/16. 3/8 and 11/16 based on the picture here in figure 5. Now the density function is equal to 1 plus 3x plus y. It's always easier, in my view, to sort of intuitively verify the center of mass if you have constant density. Okay, because then it's just easier to sort of think about where that lamina would be balanced if the density were constant. But here you don't have a constant density. The density in example 2 is 1 plus 3x plus y. But based on the figure, let's see, I'm trying to see intuitively. Well, so the density is increasing with x and y. Density is increasing with x and y. So that should pull. I mean, normally the center of mass, I might think it would, if it were constant density, I would think it would be, a little closer to the origin and down a little bit. But you have a lot, like the density is getting greater as you move towards that line segment, y equals 2 minus 2x. And so you have I guess it's heavier towards the line segment, and so that pulls the center of mass towards the line segment. And you have more space than to the left of that red dot where the center of mass is. Does that make sense, class? Does that make sense? Intuitively? Okay, John's comfortable with that. Anytime we can use our intuition, it's always nice, right? Always nice. So that's the center. That's the center of mass. And in terms of the moment of inertia, well, are there any questions before I go on? We only have a minute here, but who's reasonably comfortable? Okay, John's reasonably comfortable, and Robin, and Ryan, and Eric. Wonderful, wonderful, wonderful. Okay, and this section 12.5 is not going to be on exam 3, right? Exam 3, the 12.4 is the last section for exam 3. But let's just go down a little bit here. Okay, so let me find here. So moment of inertia, they have formulas for moment of inertia, okay, about the x-axis. Moment of inertia about the y-axis. And then, of course, you have a moment of inertia about the origin, called polar moment of inertia. And the book sort of, it gives the formulas and you apply the formulas, okay? I'll leave it up to a physics class to go into detail about these formulas, but then they have an example 4 where they talk about moments of inertia of a uniform disk. And they're letting the radius be radius A. So they're going to get some general formulas. But that being said, I'm going to stop there. It is 8:45. So you're worried now about 12.4. So let me stop the recording.